Okay, good day. This is AP Calculus. I am Mr. McCulley. This is the presentation for section 3.5, limits at infinity. Let's get right to it. All right, so today we're going to be talking about determining finite limits at infinity, and we're going to determine the horizontal asymptotes, if any, the graph of the function. So first, let's talk about the definition of a limit at infinity. So let L be a real number. The statement, the limit as x goes to infinity of f of x equals L, means that for any epsilon greater than 0, there exists some m such that the difference between f of x and the limit is going to be less than epsilon wherever x is greater than that m. All right, so, well, let's do this one. And the limit of f of x as x goes to negative infinity equals L means that for each epsilon greater than 0, there exists an n less than 0, such that the difference, or the absolute value of the difference between f of x and L is less than epsilon wherever n is less, or x is less than n. Now I know that seems pretty bizarre, and this epsilon always tends to throw people off. So let's talk about a graphical demonstration of limit. So let's just say, as a for instance, that we are saying our limit L, our limit L is this value right here. So let's erase this. I want it to be L right here. And we set some positive value, epsilon, like this. That's epsilon distance away from, oops, I didn't want to do that. So let's just erase this little bit right there and say that is also epsilon distance away. So what this essentially is saying is that if I pick some finite gap, some space here for some function f of x, and so let's say, as a for instance, we've got a function that does this, right? I am saying, and so we're saying that the limit as x goes to infinity of some f of x equals L. That means that for each epsilon, and you can pick whatever epsilon that you want, doesn't matter. It can be wider than this, it can be smaller than this. But if there is a limit, then we know that there is some value m that is greater than 0, that for no matter what m I pick, you know what, I'm just going to draw it like this, is that from this point on, no matter what happens, the function f of x, this curve, is going to stay between those two epsilons. It's never going to go past it. And so we can pick some epsilon bigger, we can make some epsilon smaller. In this particular case, if I pick epsilon to be bigger, I might have to have my m a little closer to the origin. If I make my epsilon a little smaller, I might be able to move my m a little further out, or might have to move my m a little further out. But we can say that if the limit actually exists, then for any epsilon that you pick, there has to be some m that you can say that for any value on the right side of that value m, the function is going to stay between those two horizontal lines epsilon units away from that limit. And the same can be said for the negative version as well, but we won't do that one. All right, horizontal asymptote. The line y equals L is a horizontal asymptote of the graph of f if the limit as x goes to negative infinity of f of x is equal to L, or if as f goes to positive infinity, or as x goes to positive infinity, the function value goes to L. Then there is some rules for finding the horizontal asymptotes of rational functions. That should be of, not off. I should fix that. Anyway, but these are review statements from pre-calculus when we were doing rational functions. And so they're fairly straightforward. And it says if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. So all we're doing here is comparing the degree of the numerator to the degree of the denominator. And again, this one only works for rational functions. And so if we have something other than a rational function, we're probably going to have to do something else. The second rule says that if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the two leading coefficients. And then finally, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is 0. And so again, these are just review rules that we did state in pre-calculus, so they should come back to you fairly quickly. But just as a quick demonstration, it says, what is the horizontal asymptote of any of the given function? Now this thing is a rational function. And just to review the vocabulary rational function, a rational function is a function that is the quotient of two polynomials. So this is a polynomial expression and this is a polynomial expression. And so we're making a fraction out of those two polynomials. Now the degree of this one is 2, and the degree of this polynomial is also 2 because the leading term is always the one with the highest degree, not the one that comes to the first or in front. So the degree of the numerator and the degree of the denominator are both 2. So this second rule here applies. The degree of the numerator is equal to the degree of the denominator. So the horizontal asymptote is going to be the ratio of the leading coefficients. And so let's see, the ratio of the leading coefficients is going to be 2 over -1. So y equals -2 is going to be our horizontal asymptote. And if you were to put it into your graphing calculator, and I would do that, except I still having troubles getting my graphing calculator to come up. Hopefully we'll fix that before we get to the end of this. Excuse me, water break. And we're back. Okay, the next one, evaluate the following limit. Now, this again is ratio, but it is not a rational function because it has cosine in it. And so we're going to have to be able to evaluate this thing, this function, or make this limit in a different manner. Now, the property of limits, well, at least for fractions, I could rewrite this as the limit as x goes to 0. Oops, infinity. Sorry, this is a lesson on limits at infinity, not 0. I can break this up into the two fractions. I can say it's x over x minus cosine x over x. And then we can separate that into two limits. I can say that this is the limit as x goes to infinity of x over x. And I'm going to simplify that right now of 1 minus the limit as x goes to infinity of cosine x over x. All right, now, so first off, this one's easy, this is just 1, but let's talk about this one. And first thing we want to know, what HAT is the range of y equals cosine x? Come on. What is the range of y equals cosine x? You should be thinking about that in your head. Well, the range is from -1 to +1. And so we know that no matter what value of x that you plug in there, that the cosine of x is always going to be between those two values. All right. So if I divide everything by x, and I don't have a problem with doing that, I don't have to change my signs because again, we're assuming that x is going to positive infinity. So again, we don't have to worry about that. Well, since the signs aren't going to change, and this is always going to be true, if I took the limit of all of this, the limit as x goes to infinity of negative 1 over x, and the limit as x goes to infinity of 1 over x, well, both of these things equal to 0. They're polynomial functions. So by the squeeze function, we can say that if this limit is 0 and this limit is 0, and this thing always has to be between both negative x over, or negative 1 over x and positive 1 over x, then we can say that the limit as x goes to infinity of cosine x over x must also be 0. So this thing right here is 0, so that limit is 1. All right, next example here. This one says sketch the graph of the equation using extrema, intercepts, and asymptotes. And so we're going to go through and we're going to do some of that stuff. And certainly we need to find some extrema, so that's going to cause us to talk about the first derivative. But before we do that, what can we learn here? Well, this function here can be factored, at least in the denominator, to be x minus, oops, did that backwards, sorry. Let's fix that. Equal to 2 over x. And it'll be 3 minus x and 3 plus x there. And so I can figure out what the zeros are. Well, what makes the numerator 0 will make my y equal to 0. So 0, 0 is a 0, and there's no other value for x that will make it equal to 0, so that's the only 0. And we can also find a vertical asymptote. And a vertical asymptote is wherever you get a non-reducible division by 0. And so I have two zeros in the or two values of x that'll make division by 0 in the denominator. So, and they don't factor out with anything in the numerator. So I know that I will have a vertical asymptote at x equals 3 and another one at x equals negative 3. And so let's see here. I can find the horizontal asymptote this way. Ditto sign. And I look at this thing, and the degree of the numerator is 1, and the degree of the denominator is 1. So since the degree of the denominator is bigger than the degree of the numerator, we can say that the horizontal asymptote is y equals 0. And so let's talk about y prime, because we're going to need y prime to find the extrema, because we need to figure out where the first derivative is either undefined or 0. And so the first derivative, unfortunately, there's nothing I can do to reduce this, so I have a quotient, so I have to use the quotient rule. So I've got 9 minus x squared, there's my ho, and then d high would just be 2, minus high is just 2x, times d ho is just going to be negative 2x. So woot there, all over 9 minus x squared, quantity squared. And we're just going to leave this. We're not going to mess with that, at least at this point. And so simplifying my y prime here, if I distribute my 2's, I'll get an 18 there, and I'll get minus 2x, and this thing, become minus 2x squared, and then this thing will become plus 4x squared. So negative 2x squared and positive 4x squared will give me positive 2x squared. And that's going to be all over 9 minus x squared, quantity squared. And so this thing, my critical numbers, my values that have possible extrema, well, this is never 0. The smallest the numerator can ever get is going to be positive 18. It's never 0. So I get no critical numbers for having values in the numerator. And in the denominator, the only values for x that make this thing undefined or make it to 0, we have already thrown out of the domain because they're vertical asymptotes. So we can say, at least in this particular one, Again, we have to say that the critical numbers are positive or negative 3, but because they're not in the domain, we can say there are no extrema in this one. All right. So let's talk about the graph of this thing. Well, it's not too bad. I don't like that particular line, and I should know better. So let's draw in a line here, and I don't like that. We'll fix that one up right there. Okay, let's go 1, 2, 3, 4, 5 on the x-axis. I think that'll be enough. 1, 2, 3, 4 on the y-axis. And again, 1, 2, 3, 4, -5. And so I got a 0 at 0. So right there's a 0. I'll draw that one in. I've got a vertical asymptote at -3. I've got another vertical asymptote at +3. Since my horizontal asymptote is 0, I won't draw one in. I'll just leave it there. All right, so there are no x-intercepts in this particular region over here, any value for x that's less than -3. So I really only have two choices. It can't cross the x-axis, so it's either got to start above the x-axis, really close to it, come to the vertical asymptote and go up, or start at the x-axis, underneath the x-axis, and go down. Well, let's pick a number. Let's say we pick -5 right there. -5, all right, times 2 is -10, and then -5 squared is positive 25, and then 9 minus 25 is also going to be negative, so I'll have a negative divided by a negative, so every value over here has to be positive, and at least in this region, values of x that are less than -3 have to be positive, so this graph has to go like this. Now there are two choices from 3 to 0, because it's got to at least touch at 0. It can either come down from the top and touch, or it can come down from come up from the bottom and touch there. So I'm going to do the same thing. I'm just going to pick a number. I'm going to pick, say, -2. -2 times 2 is going to be -4. So on the top, I've got a negative. -2 squared is going to be +4. 9 minus 4 is positive. So I have a negative divided by a positive. So every value in this interval has to be negative. And so I'm going to have a graph that comes up and touches 0 right there. Now, from 0 to 3, I again have two options. It can go up towards the positive infinity as it gets closer to the horizontal asymptote, or it can start at 0 and go down towards negative infinity. And again, it can't change because there's no values for x that are 0 in this interval. So it can't change. It's either above it or above the x-axis or below the x-axis. There's no way, there's no in between there. So I just pick a value. I'm going to pick 1. If I plug in 1, 1 times 2 is 2. That's positive. If I go 1 squared, that's still 1. 9 minus 1 is 8. That's positive. So I get positive divided by a positive. This thing is positive. It has to go up like this. And then my final one, it can either start at the positive infinity and come down and then go towards the horizontal asymptote, or it can start at negative infinity, come up and go towards the horizontal asymptote. But because there are no zeros or any other vertical asymptotes, it can't cross the x-axis anywhere. So all I got to do is test the value. Let's say I choose 5. Well, 5 times 2 is 10. 5 times 2 is 10. That's a positive value. 5 squared is 25. 9 minus 25, well, that's -16. That's a negative. So I get a positive divided by a negative, which is negative. So every value from -3 to infinity has to be negative. So the choice has to draw like this. And again, you can pause right here and put this in your graphing calculator, and you should get something very similar to that. All right, that's all I got for this one today. Here's the Star Wars fun fact of the day. The Imperial Star our Imperial class Star Destroyer that you see at the beginning of episode 4, the big 1976 epic classic on Star Wars A New Hope. That ship is actually considered in Star Wars canon to be 1,600 meters long. Now, to give you just a little kind of perspective, you would assume that they would at least build it similarly to how we build our naval ships today. And on the right-hand side right here, you see the USS Gerald Ford, which is the first Ford-class aircraft carrier. And it is our newest ship. This ship particular was commissioned and put to sea in September of 2016. And it is exactly 30 or 337 meters long, and you can tell if you look right here, just you can see there's 1, 2, 3, 4 decks. So just this little section right here is 4 stories high, and if you kind of extrapolate that all the way down, this thing is probably pretty close to, at least this portion here is probably 10 stories, and this is probably 5 stories about right here. So you've got quite a bit of space. So that's a really big ship, and it's not even a fifth as long as the Imperial class Star Destroyer. All right, there's enough Star Wars trivia. I hope you have a great day. Only 20 minutes long. I will see you in class. Goodbye.